Hi everyone, and thanks for being here. So today we're here to talk about Concursus, which is event sourcing for the Internet of Things. First is my colleague Dominic.
Hello.
We both work for Open Credo, which is a London-based software consultancy. And we created this thing called Concursus, and because of the limits of time, we'll try to go quickly through. So first I'll go through the main ideas, why we created it, and so on, and then Dominic will take you through a more detailed example so that you have a practical idea about how actually it works. We have a page where you can access the technical report, and all the code is on GitHub, and there are a number of really good technical blog posts that Dominic wrote that you can also find on the first page, so please feel free to do that. So first, what is Concursus? Roughly, it's a framework for processing and organizing messy data in a distributed context. So for us, it's this idea of messy data and distributed context that makes it really a good fit for the Internet of Things. Concursus uses heavily the idea of event sourcing. Who's familiar with event sourcing? Who knows what event sourcing is? Okay. So event sourcing is a technique or an architectural pattern, if you want, where all the changes to an application are captured and stored as a sequence of immutable events rather than going and changing the state in the database directly or mutating the information you have. So this is sort of a foundational concept in Concursus. When I say we deal with messy data in an Internet of Things context, what does that mean? So assume you have a number of devices and they send events to the application. I'll go more in detail in that. But some of the problems we need to deal with when we are processing and organizing the information is to be able to process these events in a very scalable and reliable way. It's the first thing we need to do. We obviously need to worry about processing guarantees and ordering. So if you have millions of devices sending events, the events can arrive once, twice, never out of order, repeated, delayed or not. All these things can happen. And what we're trying to do, as opposed to other frameworks that work at a much lower abstraction at the messaging level, is to build meaningful domain models so that developers can reason about these and build some application logic on top of that. And another very important idea is flexibility. So we assume that you collect all the data, but at that point you don't know what you want to do with it yet, or not everything you might want to do with it. So being able to change the system and add more use cases or more queries in the future is a very important idea that we try to address. Okay, practically, let's look at some of the building blocks of Concursus. It's built on top of Java 8. I think it uses Java 8 in a very sort of good and clever way to make the API really nice. We also have Kotlin integration for those who know what Kotlin is. And actually, in a few weeks, Dominic will be talking about the Kotlin integration in another conference. We use Cassandra as the main event store. As a message broker, we use Kafka or RabbitMQ. And also Hazelcast to store transient state. Now, most of these things are actually optional and can be replaced. This is the idea of a toolkit. We don't just offer an API with sort of random implementations that you can pick and choose. Depending on what you choose, you get different capabilities. And the idea is that to allow you to reuse some of the existing, maybe, infrastructure in your application organization, so to be able to evolve that. Some sources of inspiration. There's obviously the whole stream processing frameworks. But most of these, at least initially, focused a lot on the real-time analytics use case, whereas the sort of problems we use is more around building business logic in a scalable way. There were the Google papers around cloud data flow and mill wheel, and some ideas like the difference between processing time and event time and the metadata they use were very influential. Apache Spark. There's another CQRS framework, Axon, that was actually an influence as well. But what we try to do in Concursus is to try to address these concerns and blend these ideas in a way that gives you a domain model but works in a distributed way. And the concepts behind domain-driven design, as I mentioned. So why did we do all these things? there are actually 3 tendencies that motivated the creation of Concursus for us. I'll go through these very quickly. Basically, the movement from Internet of Users to Internet of Things, the movement from presence to presence, I'll go through that, and the microservices, obviously, a trend. From the Internet of Users, Internet of Things, roughly traditional web applications focus on users' request-response pattern and basically consistent interactions with the user that will take the application one step in a very sequential way. Think like a shopping trolley, okay? However, in a concept of Internet of Things, these things really change. So we basically have many more participants in an application, and we have extreme decoupling. So things are much more decoupled. We have a separation between the communication bit and the orchestration bit in the application. Even if you think about an application built with asynchronous messaging and basically where you have something like AMQP in the middle, you are decoupling consumers and producers. You still need to have in the middle a topology of queues and exchanges and so on, and your application is still coupled to that, which makes it a bit harder to evolve. So the other thing is that we decouple writes and reads. So in our domain model, multiple writes can contribute to updating the same entity, and then you can have reads that read from different events to give you a new view. We'll go through an example. All these things actually make it, these concerns are fundamentally not different from distributed systems, and this is what we realize. So we're basically bringing distributed system concerns to event sourcing and CQRS. Now, what's the problem? The problem is that many organizations, at least among our customers, are trying to build Internet of Things type of applications with the mentality or the tool set of Internet of Users. And many of them are just unable to abandon all their infrastructure or skills and so on and adopt something very as extreme as, let's say, Spark or Flink compared to what they have. And they might also be adopting microservices architectures, which makes this very hard for them. So this is one tendency. The next one is the idea moving from presence to present. So if you think about the idea of presence, it has 2 components. A space component, so we are all present in this room, and a time component, which is the present, okay? And basically, if you adopt what we call a presence model, you're coupling these things together. So how does this manifest itself? If you're basically co-locating all your app services in one container, or using an ESB to integrate your applications. For example, if you're using one global relational database to integrate your applications with global constraints, or if you're using distributed transactions or distributed locks. You basically, what you're trying to do is maintain a fiction of one global coherent present, and you move this global present to another global present by processing transactions. There are a number of problems with that. Is that, first, well, it doesn't scale at all. The other thing is just a fallacy, especially in an event sort of based model. As I mentioned earlier, you might have events out of order or repeated and so on. Then you end up with a very complex business logic that tries to maintain this fiction. So if you look at the microservices architecture or trend, actually each microservice is just an island of presence where it's responsible for a specific piece of the information, and this information is consistent within the boundary of microservices. So this is also very similar to the idea of bounded context in domain-driven design. It's the same thing, basically, that you find there. And, And even from a software engineering and architecture point of view, if you think about it, and the move to NoSQL and so on, the idea is to use specialized technologies that are really fit for purpose, for a specific purpose, rather than just something that is vaguely good at different things, like relational databases. So in a distributed system, the first thing you want to do is just to capture all the events in a reliable and scalable way. You're not trying to be perfect and do everything at the same time. So rather than having a model of presence, what we allow is a model of multiple presents, where you can actually build multiple views, and each view is consistent for the purpose you built it for. And then it makes things much easier to build applications. So this concept, we call it write first, reason later. in our model, or event sourcing actually, rather than having one global schema, what we have is an event store, and for each entity, so imagine these are different entities, we have small event histories. Now, we guarantee that the event histories are partially ordered, but we don't need to enforce global ordering across all event histories. So that's the main idea. This is opposed to a relational model where you have this massive model with global constraint that you try to update every time you have any change to your application. So we're going into the example now. This is a very simple Concursus system. Basically, you have the event store. There are a number of supporting Concursus services, but then you have two services here, and you have a number of devices. So you have a light bulb that obviously might receive commands and also might send some telemetry information. And you have a motion sensor and a camera. And the motion sensor might trigger the light bulb when people go into a room, or might trigger some security alert and switch the camera on and then send a message through your mobile. So the idea is that each service has its own present based on the same feed of events, and we can add many more without impacting them and while being scalable. So Dominic now will go into the example more in detail.
Okay, so really what I'm going to talk about is the domain model of Concursus, and I'm hoping that this all looks very trivial. It's the result of a kind of lengthy effort of simplifying and rationalizing, and it should seem obvious. It should be, well, of course it works like that. So here we have a thing, some emitter of events, and there's a sequence of events that it emits. It's a light bulb, so it's created at some point, it comes online, it gets screwed in somewhere, switched on, switched off. At the end of its life, it blows, it's no longer functional. And you can imagine running these events to some kind of a state machine, a state diagram, so that having received a sequence of these events, you can say the current state of this light bulb is it's switched on over here. You might also be interested in things like the times at which it's switched on and switched off, so you could get some kind of reading of how much time the light bulb had been switched on in total over the course of its lifetime so far. So that's your kind of basic model of things that can happen to a light bulb. So each thing in the system has an identifier, which is a combination of two things. The type of thing it is, it's aggregate type. Aggregate, by the way, is a bit of jargon from domain-driven design. It just means your kind of point of entry for information about a thing. And it has a unique identifier. In this case, it's a globally unique identifier, so it's this light bulb. Each event has a timestamp, which is the event timestamp, which is when this thing happened according to the thing it happens to. And this should be generated as close to the originating entity as possible. And it may have some additional information. So a light bulb's created, it has a wattage, it has some characteristics. When it's screwed in somewhere, this is a later timestamp, and it has another different set of parameters. It's got a location, it's been screwed in the hallway, for example. So events occur to a specific aggregate, they have a particular timestamp, and they may carry some data. So when we capture this into an event history, which is the history of all of the things that have happened to this light bulb, again, we've got our identifier over here, which allows us to locate this information, this event history, and then we have a series of entries in this history. And the thing to notice is that in addition to an event timestamp, we also have a processing timestamp, which is when our system observed this event. So there's when it happened according to the device, and there's when we actually processed that it happened. One thing to bear in mind in a distributed system is it's generally quite difficult to get a kind of a global clock. So you hope that your event timestamps are going to be consistent from the point of view of the emitting object. They may not be consistent over all of them. If you imagine you have hundreds of mobile devices out in the field, they're not always necessarily going to have their clocks synchronized. Whereas the processing timestamp is going to be the timestamp according to the system that processes events. So in summary, every event occurs to an aggregate, which is identified by its type and ID. It's got a timestamp, event timestamp generated by the source of the event, and the history of an aggregate. The event history is a log of events ordered by event timestamp, with an additional processing timestamp that records when the event was captured. So one of the challenges that we have is to deal with ordering. If we imagine we have multiple event sources, and they're all emitting events, sort of streams of events into the network, but by the time they arrive at our event processors, they've been partitioned, so events from different things have kind of ended up in different streams. They become interleaved, and they may be out of order. So the creation events here may actually be arriving after subsequent events. So we need to kind of sort all of this out into some kind of meaningful order. So somehow we need to take this kind of slightly jumbled sequence of events and sort events into buckets where the log is partitioned by the aggregate ID. Each event goes into the right history for its originating entity, and where they're ordered by event timestamps, so we kind of reconstruct the correct order for them. And one way to do this that's fairly convenient is to use the underlying data model of Cassandra. So I'm not going to talk through this in much detail, but this is the schema for a single Cassandra table that can be used to store all of the histories of all of the events in the system. And in Cassandra, you have two kinds of key. You have a partition key, which identifies the row that data is stored in, and also where in the cluster that information is stored. And you may also have a cluster key, which is used to say within a row where a particular set of data is. So you've got a kind of a two-dimensional addressing scheme for any piece of information, which row it belongs to, and then which kind of cluster of columns within that row. And you can tell Cassandra to order your events by event timestamp in descending order. So each event that gets written, it will find the partition within the data model that belongs to your particular aggregate, and it will slot that event into the event history in the right order. So you get a kind of a natural sorting based on Cassandra's own indexing properties. So how do we put this together with other pieces? Well, one way we might do it is to receive our events, log them into the event store, and then publish them out to RabbitMQ, which is a messaging system, so that other things can then do downstream processing on them. And by downstream processing, I mean things like responding to events and alerts and so on, but also building up views of entities that can be used for kind of reasoning about it, either for analytics or for users that want to come and find out about the state of the system or parts of the system. The event store is storing the total history of everything that's ever happened. Users are quite often interested in the current state of a thing, and that's a kind of a computed value based on the event histories. So we may want to compute that as we go along for certain things. We might also be interested in relationships between things, which the event store inherently doesn't capture. Each event history is a kind of a silo. There's no relationality between them. So if we want to build up something more like a relational model saying how things are related, we need to do that with some kind of a materialized view downstream of event capture. An alternative way to do this, actually there's another slide here. So one of the things we can then do once we've got the events captured in the event store is we can replay them into some kind of a state model, and we can reconstruct the state of an entity at any given point in its history, either its current state, or sometimes we're interested in time traveling and knowing what state it was in yesterday evening, for example. An alternative approach using Kafka is that we actually publish our events straight into a Kafka topic. Now, the thing about Kafka is that it maintains a durable history of, or log of things that have been written into it. And you may not necessarily keep everything forever, but you may keep a kind of a window or a buffer of events. And that's sufficient to drive multiple things off. So we can capture the events from Kafka with an event store listener and populate the event store, and also push them through to downstream processing, all of the same queue. This gets quite interesting if you want to start responding to events nearer to the edge of the system. You've got a kind of a centralized store of information which you might be using to drive analytics, and you've got a very sort of centralized view of the world. But you may also want to be doing things more immediately and kind of closer to the edges of your network. And the Kafka topic is kind of a way to mediate between those two different views of the world. It's a sort of buffer on which things converge. So it's kind of quick summary of the processing model. We've got events that may arrive partitioned, interleaved, and out of order. We sort them into event histories by aggregate type and ID. Within event histories, we sort them by event timestamp and not processing timestamp. So it may be that events arrive out of order, but the event we process later gets slotted into the history before the last event we observed. That means that event consumers need to take into account the possibility that an event history might be incomplete at the time it's read. So we might want to consider using kind of a watermark, looking at the gap between event timestamp and processing timestamp to figure out how long we need to wait for events to settle. And we also sometimes need to deal with kind of wildly out of order events, so we may actually have to change our view of history. And there are various kind of policies or strategies you can use for dealing with that. So I'm going to talk fairly quickly about the programming model then that we've built around this. Obviously, this is kind of slightly more kind of interest to developers, I guess. So the core metaphor, we've got a sequence of events that we're replaying from the event store, and we have a consumer of events, something that will receive those events and consume them. And in Java, this is literally a consumer of events. So this is a type in Java of a thing. And a consumer of events is an interface with a single method, which is accept. So we create an event, we've got our aggregate ID, our timestamp, name of the event, and some information about what happened. And we just, you give me an event consumer, and I pass it the event. Here's an event. And that's how you generate events. You pass them into an event consumer. What happens to it after that is not your immediate concern. It might get kind of routed elsewhere, it might get filtered or whatever. But your way of generating events is to pass them to an event consumer. If you want to handle an event, you implement the event consumer interface, which in Java 8 we can do with a lambda, a little function. So you have something that receives an event and does something with it. So the same interface, consumer of events, is being used on both sides for pushing events out and for receiving events coming in. The other thing that we have is quite often you have several different types of events for the same aggregate, and we gather those together into a Java interface. So for a light bulb, we have an interface light bulb events, which handles events for light bulbs, and it has one method for each type of thing that can happen. So again, to emit an event, you call a method on something implementing this interface, and it generates the event and puts it into the system. To handle an event, you implement this interface, and you are called on the appropriate method for the type of event you're receiving. So within the Java 8 mapping, we get a proxy, which proxies our interface here, and we just call lightbulb events created with timestamp and the ID and our parameters to push a created event into the system. To handle events, we have an interface, say just one with just the kind of created event method, and we have a bit of magic that kind of dispatches events to an implementation of that interface. So a lot of the real interesting work is being done by what we call event handling middleware, which is a chain of consumers of event that transform, route, persist, and dispatch events. So a single event submitted to this chain might be checked against an idempotency filter to make sure we haven't seen it before. And we might do that with something like a Hazelcast distributed cache. It might be serialized to JSON so we can send it over the network somewhere else. It might be written to a message queue topic, retrieved from that topic and deserialized. It might be persisted to an event store like Cassandra. It might be published to an event handler which maintains a query-optimized view of part of the system. Or it might be published to an event handler that maintains an index of aggregates by event property. Let's say we want to be able to look up light bulbs by wattage. We observe all of the created events, we observe the wattages and the aggregate IDs, and we maintain an index. So a lot of the interesting stuff goes on within this kind of middleware layer, and it's really a question of having all of the right sorts of pieces and knowing how to put them together. And a lot of the real work then is being done by often quite sort of commodity components. So if you push things out to a Rabbit message queue topic, you're using Rabbit's guarantees around message processing and delivery and so on. If you're using Kafka, then you're using Kafka's processing. If you're using Cassandra, you're making use of the way Cassandra orders events in storage and so on. So really the Concursus framework is a sort of a collection of bits of glue to allow you to bring these things together and make use of them to build an event sourcing system. Okay, that's it for me. Thank you for listening. Any questions?